In this video I'm going to talk about thermal noise, which is that white noise that you heard in the last video. Just in case you don't know too much about what thermal noise is, I'm going to spend some time at the beginning of this video talking about what it is and how to calculate how much of it we have in the circuit. As you might have guessed by the name, thermal noise is caused by heat. It happens in all electrical components, but I'm going to focus on resistors in this video. So the resistor is full of electrons, and these electrons are all bouncing around all over the place because they're hot. So sometimes, completely by accident, you might end up with more electrons at one end of the resistor than the other, just because they happen to randomly bounce that way. And when that happens, you end up with a voltage across the resistor. Now these electrons are usually going to be spread pretty evenly throughout this resistor, so the average voltage is going to be 0 volts. But since they're bouncing around, there's going to be some random variation around 0 volts. And that's the thermal noise voltage of a resistor. And a useful way of modeling a noisy resistor is as a perfect noiseless resistor in series with a voltage noise source. We'll call it a Vn, which changes randomly over time. And the reason it's called white noise is because it has power at every single frequency. So if you looked at the distribution of power over frequency, it's just going to be flat. So it doesn't matter what frequency you're looking at, you're always going to get the same amount of noise power. It does eventually drop off at really high frequencies, but the frequency at which it starts to drop off is way higher than anything we will ever care about. So for all intents and purposes, we can just assume it's going to be constant. And the power density in units of watts per hertz is given by the formula 4 times the Boltzmann constant times the temperature. Now exactly where this formula came from is kind of a long story, one that I forgot a long time ago, but there it is. Since the power dissipated in a resistor is the voltage squared divided by the resistance, we can plug this into our power density equation to get an idea of roughly what the noise voltage over a resistor is going to be. Now this bar above it right here means average. Since we're dealing with the average power density, what we end up with is the average of the noise voltage squared, which I'll be calling the mean square voltage. It might also be called the voltage variance. And also remember that this is not just the average power, but the average power density over the frequency spectrum. So the units are not just nanovolts squared, but they're nanovolts squared per hertz. And when you take the square root of that, you end up with the RMS or root mean square noise voltage. And the units for that are usually nanovolts per square root hertz. The square root hertz part doesn't really make all that much sense, but that's the number they usually put on the data sheets, so we got to deal with it. And from this you can see that large value resistors have more voltage noise on them. Small value resistors have more current noise on them, but since my circuit reads voltages, I don't really care about current noise all that much. So here we have a few different ways of representing this noise voltage. We could talk about it as an actual voltage that changes over time. Or we could talk about the mean square voltage per hertz, or we could talk about the RMS voltage per square root hertz. Or I could start with, say, the mean square voltage and come up with an equivalent resistance, which is basically how large would a resistor have to be to cause that much noise. And in this video I'm going to sort of be going back and forth between all of those, based on whatever's more useful to me at the time. Alright, almost there. One more thing I need to talk about is the concept of input referred noise. So let's say I have an amplifier, and there are some resistors inside the amplifier, just sort of scattered around in there. And all these resistors are going to have noise on them, which is going to add some noise to the output. And I need some way of comparing all these resistors apples to apples, so I can find out which ones are more important in terms of the noise performance of the entire amplifier. And the way I do that is by looking at one resistor at a time and finding out how much noise it's going to add to the output. And then I consider the case with a perfect amplifier with no noise, and I calculate how much noise it would take at the input of that amplifier to cause the same amount of noise at the output. And so by referring all these noise sources to the input, I can compare them all at the same place and find out which ones are more important and which ones I can ignore. And really the only important case we need to worry about for this video is having a noisy resistor at the output of an amplifier. And what we need to figure out is how big of a noisy resistor would it take at the input to give us the same amount of output noise. So we can start by saying the amplifier has a voltage gain of G, and then we can relate the output noise voltage back to the input by dividing it by the gain. And then the noisy resistor value is proportional to the mean square voltage, so we square that, and what we end up with in the end is that the equivalent noisy resistor value at the input is equal to the noisy resistor value at the output divided by the gain squared. So I think that is all the stuff we need to know to look at the noise in this circuit. So now that all the boring stuff's out of the way, let's get to the meat and potatoes. So here's the circuit again. I've got the resistor values over here and the voltage gains of the front end and the back end. I'm going to split this in half and look at the front end and back end separately. So let's start with the noise in the front end. So here I've cut off the front end and tied both of its inputs to ground, so there's no input to the amplifier. We're going to assume that both of these R1s have no noise on them, and I added a noise source to R2. Now these op amps are going to output whatever voltage they need to output in order to make the voltages at the minus input and plus input equal to each other. Since the plus inputs are at ground, we can say that the voltages at these two nodes right here, the minus inputs, are going to be at 0 volts. So, because both of these nodes are at 0 volts, we're going to have some current flowing through R2, which is Vn over R2. And because we can't have any current flowing into or out of these inputs, it's going to have to be flowing through the feedback resistors and into and out of these op amps outputs. And then you multiply that current by the resistor value R1 to find the voltage drop over R1, and it really just looks a lot like two inverting amplifiers put together. So in the end, you end up with a total voltage gain of 2R1 over R2. Now we want to relate that output voltage back to the input and say what input voltage would it take to give that output voltage. Then we do that by dividing by the front end gain, but since the gain the noise voltage went through is roughly the same as the front end gain, we can just approximate and say that it's basically the same as if the noise voltage showed up right at the input of the amplifier. And with that, I'm going to come up with what I'm going to call the effective input noise resistor, which is how big of a resistor will I need at the input to cause the same amount of noise at the output as this resistor that I'm looking at, which in this case is the same resistor value as the resistor we're looking at, because the noise voltage effectively showed up right at the input. Now let's take the noise source off of R2 and move it into one of these feedback resistors. Since both sides of R2 are at 0 volts, there can't be any current flowing through R2. So in order to make sure there's no current flowing through that path, the output of the op amp needs to have its output voltage equal to the opposite of this noise voltage in order to cancel it out. And since there's no current flowing through this path, the output of the other op amp can stay at 0. So the noise voltage only shows up at the output of one of the op amps. So the total output voltage is just the noise voltage. So it's effectively the same as that noisy resistor showing up at the output of the amplifier. And from earlier, if we want to refer a noisy resistor at the output back to the input, we divide it by the voltage gain squared. And since this is symmetrical right here, we can say that we have the same amount of effective input noise resistor coming from the other R1 too. So we've got two of these at the input. And then you can plug in all those numbers. I'm just using a gain of 20 instead of 21 because the numbers work out a bit easier. And what you find is that even though R2 is much smaller than R1, it's 10 times smaller than R1, and we have two R1s, it still has a much bigger impact on the noise of the entire amplifier than both of these R1s put together. And now we can look at the noise of the back end, which I'm just going to sort of gloss over a bit because it's pretty simple. So some of these resistors have noise sources that show up at the input of the back end, some have noise sources that show up at the output of the back end, but since the gain of the back end is 1, that doesn't really matter, and they basically all show up at the input. So here it's as though we have 400 kiloohms worth of noisy resistor all showing up at the output of the front end. And then we can relate that back to the input of the front end by dividing it by the gain of the front end squared. So if I use a gain of 20 again, because it works out better than 21, we end up with approximately a 1 kiloohm resistor at the input, giving the same amount of noise as this 400 kiloohm resistor at the output. So you can see that R2 has a much bigger impact on the noise of the amplifier than all the other resistors put together. So basically, this bastard right here is controlling the noise for the entire amplifier, even though it's only one 10 kiloohm resistor up against 6 other 100 kiloohm resistors. And that's because the noise from this resistor gets amplified and the noise from all the other resistors does not. So the takeaway from this is that when it comes to thermal noise of resistors, it's really not the size that matters, it's where you stick it. And just as an aside, it's important to note that there is more noise coming into the amplifier through this reference input here, which I'm using for DC offset correction. But since that shows up at the output, it's safe to ignore. But wait, there's more! The TLC 272 datasheet specifies an equivalent input noise voltage of 25 nanovolts per root hertz, and I have 2 of these amplifiers at the input. So total from my 2 amplifiers at the input, I have 35.4 nanovolts per root hertz. And from all of my resistors put together, I have a total of about 13.9 nanovolts per root hertz. And when you put those together, you end up with a total of 38 nanovolts per root hertz for the entire amplifier. But that's not that much different from just the input noise of the amplifiers. So after going through all that work of finding out how much noise those resistors were contributing, it ends up being dominated not by the resistors, but by the amplifiers that I'm using at the input. But wait, there's even more! Don't forget that the circuit is going to be attached to my body, which has some resistance along with it. And as far as the thermal noise goes, it does not matter what a resistor is made out of or what shape it's in, it's going to have the same thermal noise. So on a really good day, I might have maybe 200 kiloohms, which will contribute 58 nanovolts per root hertz. On a bad day, maybe a megaohm will contribute 130 nanovolts per root hertz. And either way, that's going to be bigger than the total amount of thermal noise that I have already. So the noise performance of my circuit probably doesn't even matter all that much because I'm putting so much thermal noise into it. So now let's see if the noise of the circuit actually does matter. Right now I've got the inputs shorted together. Just ignore the resistors. I'm just using the leads to short the inputs together. So now we're going to take a recording with the input volume all the way up, and there's my thermal noise on there. And now for comparison, I've got 2 1 mega ohm resistors on the inputs. Kind of hard to get it just right. I sort of have to hold on to these resistors to get good connections. Otherwise I just get a bunch of 60 hertz on there. But I think this section right here is good data. Let's take a listen to that. Yep, that's all white noise. So compare the amount of noise that we got with the short circuit to the amount of noise with the 2 1 mega ohm resistors on it. So it's pretty clear that even if I eliminated most of this noise, it wouldn't really matter since I'm attaching so much resistance to the inputs anyway. Alright, so what did I learn from all of this? First of all, I learned that the noise performance of my ECG is almost entirely dominated by the thermal noise of my body that's going into the circuit. It does not mean that all the math I did was for nothing, because now I know for sure that I don't have to waste my time improving the thermal noise of my ECG circuit, because even if I did, it wouldn't make that much difference anyway. Also, I know that the conductive jelly will probably help, since that will reduce the contact resistance at the electrodes and reduce thermal noise that way. This is also good news in terms of the RF filtering that I'm going to add next time. Any filtering that I add between the electrodes and the amplifier is going to add some more thermal noise, but I know that it probably won't matter all that much. And although I might not be able to improve the noise performance at the input, I might be able to improve noise performance at the output. Because remember, what we're finding is not just noise power, but noise power density over the frequency spectrum. Now the sound card on my computer might be recording all the way out to, say, 100 kilohertz. So all the noise power is going to get added up over that entire bandwidth. But I could add, say, a low-pass filter at the output of my circuit, and to say maybe like 2 kilohertz or something like that. And then the noise power I would have it going into the computer would be added up over a much smaller bandwidth, and we end up with overall less noise power. I'm going to have to do some experimenting to try and find a good cutoff frequency so that I cut off as much noise as possible without filtering my ECG signal, but that is one thing I can do to get less noise at the output. That's it for this video. Kind of long, but hopefully not too boring. In the next one I'm going to be adding some RF filtering to the input to try to stop any RF signals before they get into my amplifier. So yeah, leave some comments and whatnot, and I'll see you next time.